Hey everybody, so we're going to do an example here dealing with vector functions and the space curves that we associate with them. So I want to make that idea clear, and then we'll tackle this problem in particular. So this notion about space curves and vector functions we can think of as follows. Here's the origin. Okay, I'm not going to draw any axes, they get very complicated. When I have a vector function, I can imagine it, well, I'm not imagining it. What happens is we input a number and we output a vector, right? And so the outputs, if I was going to draw one particular output, might be a vector there. And then later I put in a different number and I get a different vector output. Right, so I'm not going to draw all of them, but you can imagine an infinite number of vectors pointing all over the place. If we track the points that these vectors point at, we get some kind of curve, right? And so even though they're not precisely the same thing, they are closely associated to each other, right? We've got vectors pointing at points along a curve. So that's the idea between the connection between a space curve and a vector function. So in this particular problem, we're supposed to get, we've got this vector function r of t is equal to t times cosine of t, t sine of t, and t. Those are the three component functions. And we want to sketch this curve. There's lots of ways we could go about doing this, but the problem suggests taking a look at the function z squared is equal to x squared plus y squared, and noting that this vector function lies on this curve. So we want to first show that it lies on this curve, or sorry, on this surface. In other words, that the vectors are all pointing to points on the surface, or in the language of the space curve, this curve associated to it, that curve would lie on the surface of this surface. So it would all be points on the surface. And then use that picture to help us understand what this thing looks like. So let's do that. What does it mean to say, all right, so let me name some things and let's get a general plan and then get into the details. I've got this surface z equals x squared plus y squared, right? So I'll call it the surface S. When for a point to be on this surface, a point A, B, C is on S if, well, if just like a point on a curve is, the way we know that a point is on a curve is if it satisfies the equation that we assign to that curve, or associated with that curve, if the numbers a, b, and c make this equation true. In other words, if c squared is equal to a squared plus b squared, right? That's just what it means, that it satisfies that. So to say that this curve in question lies on this surface means to say that the coordinates of the curve, any coordinate of the curve, satisfies this equation. Well, in our case, our space curve we can think of as the parametric, given by the parametric equations, x of t equals t cosine of t, y of t equals t sine of t, and z of t equals t. So to say that the points of this parametric curve lie on this surface is to say that these three component functions satisfies this equation. And let's see if this is true. I'm going to take x of t squared plus y of t squared. What do I get? I've got t squared cosine squared t plus t squared sine squared t. I can factor out t squared. I get cosine squared t plus sine squared t. Of course, that's a trig identity equal to 1. And we see that it's equal, that the sum of x squared and y squared, the component functions x squared and y squared, gives us t squared, which is, of course, the square of the z component. In other words, regardless of what value of t we put into this function, it spits out a vector pointing at a point that satisfies the equation of this surface, which means that every point on the curve associated to that vector function must lie on that surface because all those points satisfy that equation. Okay. All right, so now we know our curve lies on that surface. Let's try to think about what this surface looks like. And the way we're going to do this is with something called traces in particular. So traces are, we look at like slices of our surface, right? If you've got some surface, you can imagine, I don't know, maybe it's got a hill in the middle. You can slice it with planes parallel to the coordinate plane. So for instance, you might slice it with a horizontal plane right here, and you'd see when it intersects this hill, you get some shape. And maybe you'd imagine slicing it with a vertical plane, and maybe the way it intersects is some curve in that plane. And you can do other ones and get all kinds of different shapes, right? It's difficult to draw. I know there's some animations out there that make it a little bit clearer. But what it does is help us build the picture in our mind. I'm going to do something particular. I'm going to take slices where we let z be equal to different values. Okay, so in other words, I'm going to set z equal to a constant, right? And let's just let the letter r represent that constant. So if z is equal to a constant r, then x squared plus y squared must be equal to that constant squared, right? Well, we might recognize this as the equation of a circle with radius r. Let's just write circle with radius r. That's what these slices look like. And I'm going to illustrate what this looks like in just a minute. So this is a circle with radius r. However, notice because we're squaring z, we can go a little bit further. Instead, let's think about plus or minus r. If z is equal to -2 and 2, in both cases we get a 4 over here, a circle with a radius of 2, and so the radius is actually going to be the absolute value of r, whether it's negative or positive. Let me make that a little neater. Okay. All right, let's think geometrically about what I've just done. So this is a tricky one to draw. Let's start with an axis. So I'm going to draw in the z-axis. Okay. This is the z-axis. Let's think about letting z equal several different constants, right? So for instance, when z is equal to 0, that's our first value of r, it's a circle with a radius of 0. Well, z equals 0 is a horizontal slice right at the origin. Let's put the origin there. So at the origin, a circle of radius 0 is just a point. In other words, when z is 0, x and y both have to be 0. Let's think about z equals plus or minus 1. What does this look like? Well, if I draw a plane at z equals -1 and +1, these are going to be parallel planes. One, let me draw the one above first, actually. I think it'll be a little easier. So first I'll draw a plane at z equals 1. And then there's one below it at z equals -1. Right? So this lower plane is hitting at z equals -1. This upper plane is hitting at z equals 1. In those horizontal slices, x squared plus y squared equals 1. We're squaring the z component, meaning the slice looks like a circle of radius 1. So here we get a circle with radius 1, and below we get a circle with radius 1. We're pretending those have the same radius. The drawing's not perfect. All right. Every time we change the value of z, if I go up to z equals 2 or 3 or 4, right, I can draw more planes and slice that. I'm not going to keep drawing planes. This drawing will get horrific. But what we imagine happening is every time we slice it, we get circles whose radius is equal to the z coordinate. And we get the same thing in the downward direction, just with the absolute value applied. All right, that drawing's not looking great. But if you imagine a shape that's just a point in the middle, 0, 0, 0, and every time we slice it, we're getting circles getting bigger, and as we go down, we're getting circles getting smaller. We can imagine something kind of like an hourglass, but very angular, right? The sides of it are these would be in profile would look like the lines z equals y, or z equals x and z equals negative x, or z equals y, z equals negative y, depending on which way you're looking at it, right? That's the surface represented by the equation we were given. Z squared equals x squared plus y squared. It's not a great drawing. We're going to go to a graph in a few minutes, but I want to see how we could get through this if we didn't have that. It's a good way to build our intuition, try to draw these things. Now, that's not what we're after. We're after the actual curve. So let's look at our equation. We've got it in parametric form here. Let's just look at x and y. If we look at the x and y coordinates, so this means we're not thinking about its height, we're just thinking about its horizontal, the two horizontal positions, right, in the xy plane. In other words, I like to think of it as like, if we ignore the z component of its position, it's its shadow. We're thinking about what its shadow does on the xy plane. Well, we know what cosine t and sine t do. If we're in 2 dimensions and we have x equals cosine t and sine t, we get something that spits out a circle rotating in the counterclockwise direction, right? However, we've got that t in front. What does that do? Well, normally the circle starts right here because it's got a radius of 1, and that's the cosine of 0 is 1, the sine of 0 is 0. We start out at this point. However, we're multiplying by 0, which gives us a radius of 0. As we increase t, we're wanting to follow this circle, but our radius is starting at 0 and slowly growing as we go around. And so we're going to get this radius that's getting larger as we move, as we go in the positive t direction. Right? Similar thing happens in the other direction, except we get negative, which reverses our angle. So what this thing ends up looking like, now we're going to add in the z coordinate. The z coordinate just goes with t. So as t goes up, our z coordinate goes up. As t goes down, our z coordinate goes down. And what we end up with is this spiral wrapped around this curve, or this cone, okay? Now, the point of this is not to get a perfect drawing, right? It's very difficult to draw. The point of this is to start thinking about these ideas and trying to picture them so that we can get a more intuition around how these things work. But let's take a look at, let's go to a program to look at some graphing software to look at what this actually looks like, or a better picture of what it looks like. So here's our XY plane. Here is that cone. And now here is the curve, right? So I don't have it graphed to infinity, so it stops, but in reality, it keeps going. And we see this curve that's laying right on top of that cone, coinciding with the surface of that cone, slowly rotating around it in either direction, with the radii getting larger and larger the further away from the XY plane we get. And so without the surface there, it's not quite as easy to see, but it's still wrapped around that cone, and we get this kind of odd spiral, right? It spirals one way above the x-axis and a different way below, or sorry, the xy plane, and one way differently below because of the negative. If you remember your trigonometry or polar coordinates, when you get a negative radius, it points in the opposite direction of the angle. So it kind of reverses how this thing is spiraling. But I mostly wanted us to be able to picture the surface and get the notion that this is a spiral attached to the outside of this curve. Okay, that is it for this one. Thanks, everybody. I will see you next time.